Welcome to the fifth and final video in Unit 5. We've been talking about SNAc reactions for a while now, but what I want to focus on in this particular video is the concept of catalysis, or how we could actually use compounds that will accelerate any kind of SNAc reaction in principle. There's a lot of details associated with how to choose catalysts that we really won't talk that much about in this class. Really, we're going to focus on some basic concepts and principles for catalysis in these kinds of reactions. And I also want to underscore that the types of principles that we'll develop in this video are going to be relevant for other classes of reactions we learn later in the semester. So please don't treat what we're going to do here as just relevant to SNAc reactions. Treat this as a broader concept of how reactions can be accelerated. I want to do this in the context of an example. So we're looking at a reaction where we have a methyl ester and ethanol. So notice the Me versus the Et. And we could exchange those two groups. So the ethanol would serve as our nucleophile, the OMe group would be our leaving group. We know that this compound, if it's our nucleophile, would be one of our neutral protic nucleophiles. So this proton gets transferred to the leaving group. And we end up with structures that look like this. So we make an ethyl ester, notice the Et, and methanol. This is what's called a transesterification, which means we're taking one ester and turning it into a different kind of an ester. These reactions definitely work, and in some cases they're important for us. But one thing we might notice is that we have an electrophile that's not a very good electrophile. We know our oxygen here is a powerful resonance donor. This group is an overall net donor, and that makes this a weak electrophile. And if we analyze the structure of our proposed nucleophile, our ethanol, I'll draw my lone pairs in, we notice that this compound, the lone pairs on the oxygen are pretty highly stabilized. The oxygen is not charged. Oxygen is extremely electronegative. So these lone pairs are probably fairly stabilized. We could confirm that by looking at pKa's for the conjugate acid of this compound, where there would be another hydrogen on the oxygen and the oxygen would be positively charged. That pKca is about 0. So we know that this lone pair is highly stabilized. We have a weak nucleophile. And what we end up finding in this situation is that we'll have a very low rate. And this rate will be slow in both directions. So I want to be clear, we're not talking about an equilibrium constant right now. We're not saying like, will the right-hand side or the left-hand side be favored? We're essentially saying, like, how feasible is it, or how long will it take for our nucleophile and our electrophile to like actually react with each other? And it turns out as our nucleophile and our electrophile become weaker, the reaction rate slows down. We talked about this a little bit in an earlier video where we talked about how you could use a powerful nucleophile and a weak electrophile or vice versa, and those reactions can have reasonable rates. But a lot of SNAc reactions, this is an issue, especially with things involving like esters or amides, things that are very weak electrophiles at the carbonyl center. So to speed these reactions up, or to accelerate them, we need to adjust the strengths of our roles. So we're going to change strength of at least one role. And just to remind you what I mean by roles, that was cool. We're talking about electrophiles and nucleophiles. But more concretely, we could say, well, maybe we could make some structural change that would make our nucleophile stronger, or without changing its structure permanently. Or maybe we could actually make some change to the electrophile structure kind of temporarily that would make it more electrophilic. So another way of thinking about that is turning up the dimmer knob on a light switch. It's not that you're like doing something fundamentally different with your source of elimination, you're just making it brighter. Now, there's a variety of ways we can do this. If we want to increase electrophilicity, what we know is that we need to make whatever center that we're treating as our electrophilic site, so in this example it would be the carbonyl carbon, we need to make it more partially positively charged. We need to destabilize that positive charge. So increase partial positive on our electrophilic center. And if we're going to increase our nucleophilicity, we're going to use a very similar tactic. We want to destabilize the lone pairs or a lone pair on any of our nucleophilic sites, for instance. So one way to do this would be to increase charge, make it more negative. There's other features you could think of as well that might be destabilizing. For this particular kind of reaction, where we'll talk about SNAc catalysis, we'll stick to increasing partial negative on our nucleophile. I'll just spell it out, nucleophilic center. Or in an ideal world, we could do both of these at the same time, and that should greatly increase the reaction rate because now we've got two powerful reactants that are motivated to change with each other. So we're going to talk about each of these kind of permutations in isolation, because it turns out that unless you're working in a biochemical context with enzymes, it's almost always going to be the case that chemists have to choose one or the other. So we're either going to make a better electrophile or we're going to make a better nucleophile. And the choice for what you would decide, which of these strategies you would use, is a highly complex one. So again, this is not something that we're going to talk about in detail in this semester, more focusing on the strategies that we, or rather the tactics that we would use to actually make these strategies come to life. So we'll tackle making our electrophile better first. To make better electrophiles, chemists will often use what's called acid-catalysis, which involves adding a proton, or more realistically, a source of H+, to a reaction. Often those choices would be among strong acids like sulfuric acid or HCl. We're not going to talk over much about how you would choose one acid over another, but know if you see things like H2SO4, for instance, sulfuric acid, in a reaction, and especially if it's labeled as cat or catalyst, or if you see something like H plus cat, we're likely dealing with a situation where we're trying to make our electrophile better. So we can make better electrophiles with acid catalysts. This is a really general statement. We're going to see the same principle with different kinds of functional groups, so not just carbonyl-containing compounds throughout the semester. This is one of these kind of concepts, a little bit like the relationship between pKa and conjugate base stability. I'd strongly encourage you to memorize. This is also one of the kind of key cornerstones for enzymatic catalysis that you'll see in biochemistry as well. So let's actually look at how acid catalysis works in the context of a transesterification reaction in a mechanistic way, because I think that will actually show us in a meaningful sense like why it is that this statement's true. So our acid-catalyzed SNAc mechanism. And to be clear, the mechanism that we're going to see here will be very similar, if not the same, regardless of the carboxylic acid derivative and nucleophile. We're just going to show this mechanism using a specific reaction, this transesterification. So to start, I'm just going to draw all my components in. I'm going to draw all my lone pairs. I'm going to use just one color for this. And I need to decide which of the atoms with lone pairs is most likely to bond to the H+, which has come from the catalyst, right? And it looks to me like all of these oxygens are probably about as basic as each other. I'm not seeing any real significant structural differences that we've talked about so far. But I also know something about the reason we added the H+. And that's that we're trying to do something to this compound, the electrophile. If we think about protonating our oxygen on the nucleophile, we actually make the lone pair go away, right? We use it to actually bond to the H. So we could think about using the oxygen lone pair from the carbonyl oxygen to bond to the proton in an acid-base step or a proton transfer step. So I'll abbreviate proton transfer, PT. And the structures that we get are kind of interesting. So one of the lone pairs on our carbonyl oxygen is gone. Our methoxy group hasn't changed, and our ethanol has been a spectator to this change. So this is our initial equilibrium, but let's actually analyze the structure of this protonated carbonyl in terms of electrophilicity. So I can draw a resonance structure here. Where I've simply moved electron density from the CO pi bond onto the oxygen, and that neutralizes the oxygen charge. So this is probably a minor resonance structure. We've seen this before, and also unit 4, excuse me. And we know that as we actually make the oxygen negative charge more stabilized, that we actually get more of this positive charge character developing on the carbon, and that increases electrophilicity. Well, stabilizing this oxygen in the minor resonance structure is really what the acid does, right? So protonating this carbonyl makes it a lot more electrophilic. much more electrophilic than when it wasn't protonated. So if you compare like a protonated ester to an ester, way more electrophilic than the normal ester, I suppose, because of this fact that we are now placing positive charge on the molecule, and that's going to be at least partially distributed onto the carbon in a much more significant way than would have been true for the unprotonated form of the ester. So if we then think about this carbon here as being our electrophilic site, and we're making it quite partially positively charged, it might make sense now that even a weak nucleophile like ethanol could donate a lone pair into a new bond to this very highly partially positively charged center. So that looks like an addition reaction. So the first step of the actual addition elimination SNAc mechanism. Draw the structure of our tetrahedral intermediate. So we've got our methoxy group attached, we've got our methoxy group attached still, lots of lone pairs. One thing that's important here, the proton has not come off the ethanol yet. It's still bonded to the ethanol oxygen after this new CO bond has been made. So we see that we now get to our tetrahedral intermediate. I'm going to need the space below, so I'll erase my resonance structure here. Here's our TI. And I know that the next thing that's going to need to happen is for, in the forward sense, for the methoxy group to leave. I know that I'm going to break that off of the molecule at the end of the day. But if I'm looking at this structure and I thought about just like breaking the CO bond, I'm going to have an O-, which isn't that great. It's a somewhat stabilized negative charge. Most of the time this reaction should just go backwards, because actually breaking this CO bond, where I just get a neutral oxygen, should be way better. All right. But we actually have another proton transfer step here. The proton that came in as part of the ethanol is basically going to be bouncing around between all three of these oxygens in the tetrahedral intermediate. So sometimes that proton ends up on the methoxy group. Sometimes it's on the OH, sometimes it's on the OET, but when it ends up on the methoxy group, something interesting happens. So I'll redraw my intermediate after this proton transfer step. So if I look at this tetrahedral intermediate now, proton transfer, I notice that by far, this is the best leaving group in the molecule. I made that the best leaving group by virtue of protonating the oxygen. You might have seen this before when you talked about additions and elimination reactions in OChem 1, where you could dehydrate alcohols into alkenes by protonating them. That makes the protonated oxygen a good leaving group, and that gives rise to your carbocation, so on and so forth. We see the exact same concept here. We can actually take this proton and transfer it to the methoxy group. That makes a really good leaving group, and now I'm set up to actually do the elimination step of the SNAc you're seeing here. So here's our elimination. I'm going to abbreviate it, elimination. And we know now it's much more reasonable to break this CO bond, because when I do so, I neutralize an oxygen atom. That's going to be way better than trying to kick something out this O-, for instance. So I'm going to show this as the hydroxy group donating electrons into a new CO pi bond, but that's just to draw the major resonance structure of the product we'd be forming, which will look like this. And it looks like I've got methanol in its entirety now. So I'm done with one of my products, homie. And then this is the structure I drew. This second bond between oxygen and carbon is coming from the donation of the lone pair on oxygen down to this carbon. You didn't have to do that. We could have left that out, in which case we'd have a carbocation. That'd be the minor resonance structure of this drawing. Yeah. And then the last thing to do, because this reaction is catalytic in acid, we would need to get the proton back. Remember, the catalysts are not consumed in a reaction. Their structures don't change from the very beginning to the very end. In the middle, their structures absolutely will change. But at the very end, they need to have the same thing you started with. So we have another proton transfer. And that we're going to show is the proton is falling off. Realistically, that's probably not what happens. Realistically, This proton probably gets directly transferred to another molecule of ester. But from an accounting perspective, it's okay to show it like this, I think. And around we go. So this looks like the products, ethyl ester, methanol, and now our catalyst back again. So we can see that we have what looks like a normal SNAc reaction, an addition step here, so our nucleophile adding to the carbonyl carbon to form a tetrahedral intermediate, and an elimination. So this looks like a SNAc, but we have proton transfers in 3 different places, right? Here at the onset to make a better electrophile. So make better E+. In the middle to make a better leaving group, right? Make our better leaving group. And at the end to regenerate the catalyst. So H+ actually does quite a bit of work here, right? We both make our initial electrophilic center better so that we can actually form the tetrahedral intermediate, but it also accelerates eliminating the group that we need to eliminate in the middle of the mechanism. Pretty clever, yeah? It may not come as a surprise that if acid catalysis is one of our options, that base catalysis may be another. So I'm going to show this transesterification under base catalysis in a very general way, just describing the base as B-. I'm not going to define the structure of the base just yet. We'll talk about that after we've had a chance to discuss the tactic here and actually go through the mechanism in a generic sense. So what we know is it's unlikely that we'll be able to deprotonate this compound, the electrophile, and moreover, if we did that, deprotonation ends up moving electron density into the molecule, right? Remember that deprotonation means you take a proton, but you leave the electrons. That's not what we want. That would actually make this electrophile worse. Instead, we're going to actually try to remove a proton from our nucleophile, and that will localize charge, which should make the nucleophilic site, in this case the oxygen, more nucleophilic. So our kind of general statement would be that base catalysts make protic nucleophiles better. This term protic is important because if we're using bases, then we would need to actually be able to remove a proton in order for the base to do what it needs to do. Let's look at this from a mechanistic perspective. So a mechanism for base catalysis. And just a reminder, like the acid catalysis mechanism we saw, we're going to look at it in the context of a transesterification, but the same concepts and steps would apply for essentially any SNAc reaction that was base catalyzed. So we'll start with our set of reactants. And our generic base, which I'll just call B-. I'll draw a lone pair. And like we talked about, the first thing we'll do is remove a proton from our protic neutral nucleophile. So that's another one of these proton transfer or acid-base steps. My electrophile hasn't changed at all in this first step, but my nucleophile has. I now have a buildup of electron density on the oxygen that has the ethyl group attached, right? So our O- is now a much better nucleophile than the neutral version that we had previously. And we also will have the conjugate acid of our base catalyst, which will now be neutral, given that it started out as a negative charge. So the next step is we have our better nucleophile that can add to the carbonyl in the way that we've seen in SNAc reactions before. So just like the acid catalysis part or mechanism, we have first a proton transfer that changes the reactivities of our species, not the roles, just how much they are of those roles. And then we have what looks like a normal SNAc. We've got an addition that will give rise to a tetrahedral intermediate. So I've got those structures. I'm going to put lone pairs in. And HB is just chilling. Conjugate acid is watching this all unfold. In this situation, I already have a negative charge on oxygen. So unlike the acid catalysis mechanism, I don't necessarily need to be making a better leaving group. Normally, we don't think about like OH- or OAT- or OMe- as good leaving groups. But here, the negative charge is already baked into the cake. So I don't pay the same tax or the same penalty for ejecting a negative charge. If I look at the other side of this equilibrium that I'm going to show for elimination, which I think I'll have to bend around the corner, I'm going to have O minus again. So O minus versus O minus is going to be much less of a problem than going from something that's like neutral or even positively charged to something that now has a negative charge in it. All right, and that's our elimination. So again, we've got a normal SNAc looking process, additional elimination via tetrahedral intermediate, which we'll label. Okay. And then the last step here, a lot like the acid-catalysis process, was to regenerate the catalyst. To do that, we'll use our leaving group, which is now anionic. In this case, it was ONU minus. It could be like Y minus in a more general sense. To remove the proton from the conjugate acid of our catalyst. And if I look at the products of this final proton transfer step, I now have our ethyl ester, so that's what I know I was going to make at the end of the transesterification. I have methanol now. And I have B minus again. So I've regenerated the catalyst. Well, if we go through this again, we see in our first step, we're making a better nucleophile. And here we're regenerating our catalyst. So once again, the key difference between acid catalysis and base catalysis is with base catalysis, you're not altering leaving group abilities, whereas in acid catalysis, you do. All right, so far we've been doing this in a very general way. We need to choose catalysts here a bit more carefully. It's not like, oh, just throw a strong acid in, it's fine. We actually need to think about an acid-base step here, which is going to be somewhat reasonable, which means we need to think about pKs. So often what we will do for these kinds of transesterification reactions, rather than B minus, for instance, is use either a little bit of the conjugate base of the nucleophile, like maybe 5% by moles of what you actually throw in terms of ethanol. So it could be like OET minus. That's one possibility. You can also use small amounts of the leaving group that's already been deprotonated or negatively charged. So we could use OET minus or OME minus. And there are other options as well, but these are kind of the most common ones for esterifications and transesterifications. You'll notice that OH minus is not actually showing up in this list, and there's a reason for that, because we get different kinds of reactivity. Even though that would work, we end up forming other kinds of products in addition to, like, for instance, transesterification. In the next section of this video, we'll actually look at what happens when we use OH minus, for instance, as a catalyst. And we'll see some other situations where this might be relevant under acid catalysis conditions as well. If we take compounds like esters, for instance, or amides, or other kinds of carboxylic acid derivatives, and react them with hydroxide, either as a stoichiometric amount of compound, so like 1 mole of hydroxide for 1 mole of ester, or as a catalyst, something a little bit different happens. We call these hydrolysis reactions, which is a little bit evocative. It sounds like we're going to be breaking something apart using water. And what we find is that you would do, it looks a little bit like a normal SNAc reaction, where a hydroxide can function as a nucleophile. It's not just a base. And that would give us a carboxylic acid. So we're going to exchange the nucleophile for the leaving group piece and OET minus. But if we look at these two compounds, we've made something that's fairly acidic, right? Carboxylic acid pKa's are around 5. And we know the conjugate acid of this is an alcohol with a pKa of about 15, which tells us that if these compounds see each other, which they will in this reaction, they'll actually undergo an acid-base reaction to form these species, the carboxylate, so the deprotonated form of a carboxylic acid, and ethanol. So what you would actually isolate from one of these base-promoted or base-catalyzed hydrolysis reactions look a little bit different than what you would expect using the SNAc reaction kind of general scheme where we just trade OH for OET. Right? There's this acid-base chemistry at the end. which is actually kind of counterproductive. In a lot of cases, what we would do is make this compound, and then as part of our extraction or workup, we would maybe add some acid to put the proton back on. You can also do hydrolysis reactions under acid catalysis. So acid-catalyzed hydrolysis. We'll look at it in a similar way, so using an ethyl ester. Again, this would be true for any carboxylic acid derivative, but we're just going to look at esters as one example. And so here, hydrolysis, I probably need water. But I also know that water is not a good nucleophile. It is a nucleophile, but it's not a good one. And I also know that our ester is an electrophile, but not a good one. So if I actually add proton catalyst, some kind of strong acid, for instance, now I can make my electrophile better, and water can actually do the chemistry as a nucleophile. What we end up with is a carboxylic acid. And we end up with ethanol. So here we don't get these deprotonated final products because, well, we've got a bunch of acid present, so we're not necessarily going to be generating a lot of negative charge. Two different ways to do hydrolysis reactions. This is really important. One of the ways that we make soap, for instance, is the hydrolysis reactions of fatty esters that come from, for instance, animal fats. If you've ever watched Fight Club, this is a central component of the theme of Fight Club, these hydrolysis reactions. So there's one other kind of process that I want to point out that looks a lot like a hydrolysis reaction, but run in reverse. So reverse of acid-catalyzed hydrolysis. So I'm just going to take these two things and I'm going to flip them around. Carboxylic acid and alcohol will be on the reactant side. I'll choose an ethyl alcohol, but it could be others, methyl, isopropyl, whatever. And some kind of an acid catalyst. And what we'll end up forming is an ester and water. So this looks like an esterification reaction. We're making an ester from a carboxylic acid. So why we call these things carboxylic acid derivatives, remember? This has a name, though. It's named after the chemist that actually developed this chemistry. It's called a Fischer esterification, with an SCH because German. It is a SNAc reaction. I showed you essentially the Fischer esterification mechanism earlier in the video. The only difference is instead of a transesterification where your starting electrophile was an ester, it would be a carboxylic acid. This is a really useful reaction. It's probably one of the best ways to make esters. In some cases, especially in simple molecules. One thing you'll notice, though, is that it is, like I said, the exact reverse of an acid-catalyzed hydrolysis. So how could it possibly work? Like, which of these reactions would happen? Do I go forward or backward? That's a really good question. The issue you're going to face is that these reactions are reversible. And they have KEQs that are usually close to 1. Not exactly 1, but we don't have a strong preference for one side or the other because if we use the tools for assessing reversibility or favorability of SNAc reactions, we find no obvious differences. I've got, like, for instance, this carbonyl versus this one, so resonance donor on oxygen, resonance donor of oxygen, not that different, right? We've got the lone pairs on an oxygen of an alcohol versus the lone pairs of an oxygen on water, not that different. pKa's, protonated form of this, so the conjugate acid, around 0. Protonated form of this is H3O+, pK of 0. Not that different. So the way we get these reactions to work, either an acid-catalyzed hydrolysis or the Fischer esterification, is to use Le Chatelier's principle. So we avoid low yields by using Le Chatelier's principle. That means that either we're going to be removing a product or adding a bunch of reactants. So we're kind of pushing the reaction one way or the other. Let's look at the Fischer esterification. There are two ways we could do this. One is we could add like a huge excess of alcohol, maybe use it as a solvent, for instance. So there might be thousands of molecules of ethanol for every molecule of carboxylic acid. In that case, I'm going to be making, well, one equivalent of water because that comes from this group here. But then I'll have all this alcohol left over, and that puts pressure on the reaction to move toward the ester. If I wanted to do the reverse, if I wanted to do a hydrolysis here, I would do the opposite. I'd add like a bunch of water, for instance, and that would push it the other way. The alternative, and this is especially relevant for Fischer esterification, is to remove the water as it forms. And that's going to pull this reaction through the equilibrium. So for the Fischer esterification, that's actually, we do both. So we use an excess of our alcohol and we remove water. There's a variety of technical ways to do that involving Kulik and glass setups and such, but we'll unfortunately not really talk about that in this video. So what I want you to take away from this conversation is really those big statements that acids tend to make electrophiles better. As a caveat, or I guess an addendum to that, they make leaving groups that can be protonated better. Bases do something very different. They make nucleophiles better by removing hydrogens from those nucleophiles, right? So we'll see those themes again and again and again throughout the semester, and you'll definitely see them when you talk about enzymes in biochemistry. Get used to them now. The other thing I wanted to introduce in this video was the concept of hydrolysis reactions, as well as the Fischer esterification. These are all SNAc reactions, right? We're using water as a nucleophile. You should be able to predict, using the general form, more or less what the structures of these products would look like anyway, regardless of whether you had seen these. So the wrinkle here is what happens to the final product under base conditions, right, that you actually remove this proton. And also to just illustrate this concept of a Fischer esterification. You're likely to hear this name. I think there's a lot about it that you're going to be doing. So just so you know, that is a SNAc reaction. It's acid-catalyzed, and it looks just the way you would expect.